Okay, so to pick up where we left off, we solved this problem and we were going to move on to the next rule.
Yep.
So we're going to go onto a blank board again. So the next one is number 2, when we are solving for final velocity. From our initial velocity, acceleration, and time. So to do this, we're going to look at some equations we already know. So we know that acceleration is equal to change in velocity over change in time, which you can also write as velocity final minus velocity initial over change in time. Okay. So really, all we're going to do for this one, we're not actually going to substitute any other equations in. We are just going to manipulate this to get final velocity by itself. So if we multiply both sides by change in time, then we get the equation acceleration times change in time is equal to velocity final minus velocity initial. And that's just, taking change in time times this side and times this side. And then we can just add velocity initial to both sides to get velocity final by itself. Velocity final is equal, and I'll write this nicer because this is our final equation. Velocity final is equal to velocity initial plus acceleration times change in time. So that right there, that's our final equation.
I made the same mistake twice in a row where I put the equal instead of a plus.
So now we're going to run a problem using this equation. And that problem will be a barge moving with an initial velocity of 1.00 meters per second is going to uniformly accelerate so that in 30 seconds it has traveled 60.2 meters. They want you to solve for acceleration using that formula that we just did. So essentially we manipulated this formula and then now they're saying you can manipulate it back to its original acceleration form.
I thought you were reading it.
It's unfortunate that they've only said speed here, but remembering that we're just doing one-dimensional motion, the direction of the velocity is not always critical for the questions, and in that case they'll sometimes just give you a speed. So to solve this problem, we're going to look for what we need. We have been given an initial velocity. Forgot to change it into writing mode. An initial velocity of 1.00 meters per second. I must have skipped doing it. This is the example problem for the next equation. I must have not done an example problem for the previous equation because it was basically just a manipulation of the acceleration equation.
All right.
Sorry to mess up your pretty notes.
It's okay.
Okay, in that case, back to a blank screen. Okay, so the next one, which is how I caught that I had the wrong example problem. The next one is finding displacement without having a final velocity.
Displacement,
So we're solving for displacement, but we have not been given a final velocity, which for all of the equations that we have had so far, we have needed a final velocity in order to find a displacement. So this equation will not include one. And this is because we know from our first equation that displacement is equal to 1/2 of our velocity initial plus our velocity final times our change in time. And we also know from the second equation that velocity final is equal to velocity initial plus acceleration times change in time. So, because we have solved for velocity final in this problem, we can sub that velocity final into the other equation
And make it really ugly.
and then we'll simplify it.
Okay.
Then we'll simplify it so it's not as ugly. We're going to make it really ugly, and then we will have an equation for displacement that does not require you to have a final velocity. So when we substitute velocity initial plus acceleration times change in time in for velocity final, we get an equation that looks like this. Change in x equals 1/2 velocity initial plus velocity initial plus acceleration times change in time times change in time. As you said, not the prettiest equation. It's about to get uglier, though.
Oh my God.
It has to get worse before it can get better, okay?
Oh.
Okay, so wipe the screen. When we distribute that, because we have to get rid of that 1/2 outside of the equation and the time outside of the equation. So when we distribute, what we wind up with is change in position or displacement is equal to 1/2 of 2 velocity initial times change in time plus acceleration times change in time squared.
Okay, so we distributed change in time.
Mm-hmm. Yes. So at this point we were distributing change in time. Don't worry, we're going to deal with the 1/2 here in just a second. Now, when we, of course, distribute the 1/2, then what we wind up with is displacement is equal to velocity initial times change in time plus 1/2 acceleration times change in time squared. And that is our final equation. Not super pretty and super neat, but also not terrible.
Can I put parentheses around the 1/2 a time squared? Can I put it over 2 or
Yeah, I believe you should be able to do
some
that.
symbol of this is
Yes.
half, not that?
Yes. Yeah, you should be able to put it over 2. This obviously also gets even prettier if you start at rest, because then the entire first section there after the equal sign goes away, because if velocity initial is 0, then that whole piece is done away with. So it can get even neater.
I could copy and paste them here.
Yes. So now we're going to do that example problem from before. The barge, moving with a speed of 1.00 meters per second, increases uniformly so that in 30 seconds it's traveled 60.2 meters. What is the magnitude of the barge's acceleration? By clarifying magnitude, they're telling you that you don't need to include a direction because they didn't give you a direction. So magnitude would be just the numerical value.
Okay. And we're finding acceleration. I thought we were finding displacement.
Well, we're using this equation, but we're using it to solve for acceleration because we've been given a displacement.
Okay.
So, if we're looking at this in terms of what we know and what we don't know, we do know a displacement. They gave that to us. It's 60.2 meters. We do have a velocity initial, 1.00 meters per second. We do not have a velocity final, but we don't need it because this is the equation that doesn't include it. And we do have a change in time, which is 30.0 seconds. But what we don't have is an acceleration. That's our missing value. So we can still use this equation, we're just going to be solving for acceleration, which, being our only missing variable, is possible for us. If we were missing another variable like time, that would not be possible. So there's two ways you can go about this. You could manipulate this equation to get acceleration by itself. I find that with equations that are this complicated, that begins to become a problem, and we're better off plugging in the numbers that we do know and then running the math.
Plug and chug.
Yes, that is my personal preference. Of course, I respect everyone's different preferences for math, so if you want to rearrange the equation, you can, but the way I would solve this is to go ahead and put the numbers in. I would say 60.2 meters is equal to 1.00 meters per second times 30 seconds plus, and I'm gonna run out of room here, so I'm gonna go down onto the next line, even though that doesn't look great. 1/2 acceleration, which we don't know, times change in time, 30.0 seconds squared. Okay, and so then we're gonna have to do the math. Let me wipe my screen and we will try to get some of this simplified here. Probably should have done this initially. So the 1.0 meters per second times the 30 seconds is going to come out to be 30 meters, because the seconds will cancel and we'll be left with meters.
We have 3 significant digits.
Yep.
So the seconds cancel. In my head, they become squared and the meter's still there. So what?
The reason they cancel is because we have we're essentially saying 1 meter every 1 second when we say meters per second times 30 seconds. So the seconds cancel like that. And that's why we are wind up with 30 meters.
Per second. 30 seconds. Okay.
If you're going 1 meter every second and you go for 30 seconds, you're going to go 30 meters.
Yep.
So we wind up with 30 meters, and then to add to that, we're going to have to do 1/2 of the acceleration. So we're still gonna wind up with 1/2 acceleration, because we haven't fixed that yet. But then we can also take the time squared. So if we do 30 seconds times 30 seconds, what does that come out to?
Probably like.
So that does come out to be 900 seconds squared.
Oh, seconds squared. I was like, it's not still squared. We just did that.
Yep. And then, but we're going to want to take that times 0.5.
So does that get rid of the half? Or is it still half A?
It's still half acceleration. We're not messing with that just yet. Plus 450 seconds squared. Okay, so now we're going to want to start moving things around.
Is it addition
Or sorry, it's not addition.
Okay.
You're right. I don't know why I put a plus sign there. Force of habit between things. It's not addition. That would mess us up if it was addition. So now I still need my eraser because I got to get rid of this mess up here. Okay, then we're gonna go ahead and let's get the meters all on the same side. So let's get rid of 30.0 meters.
So 30.2 meters?
Yep. Although, No, I don't think we should have distributed the half yet. I think we should have left it. I think we should have left it 900. That's my bad.
I did write it as a separate step because of that, so that I could like cross it out.
And then we're going to divide.
Divide
By 900
900.
seconds squared. So when we do this math, we will, I'm going to wipe my screen, but what we'll wind up with is 1/2 of the acceleration is equal to 0.03355, and then the 5s repeat off into oblivion. We don't want to round it just yet. We want to wait until we do the last step of this, which is we still have 1/2 of our acceleration, which means we got to take both sides of the equation times 2. So our acceleration will be double of what we just did. And when you get that, you wind up with 0.067111 and so on.
So you don't round until the end of the equation if you can?
You want to save as many spots as you can, keeping in mind where your other significant figures were at, but save your rounding until the end. And then we need to put this in the correct number of significant figures, which if we look at the initial problem is 3. So that's our third significant figure. So it should be 0.0671 meters per second squared.
Shouldn't we only have 3 significant figures?
Yes, we do only have 3 significant figures. Those first 2 zeros are not significant.
Yes.
If you want to get rid of the zeros and make yourself happier, which I think it looks nicer to put 6.71 times 10 to the negative 2 meters per second squared. You can write it in in scientific notation.
Yay.
There's your answer to the problem.
Woo!
Woohoo!
That one was a long one. The others weren't that long.
Yes, that one was a long one. I agree. All right. Wiping the slate clean and moving on to the last rule. And this rule number 4 is for solving for final velocity. I don't know why I just drew a 4 again. When we do not have a change in time. So we should have everything else, but we don't have a change in time. So we're going to start by multiplying our very first friendly equation by 2. So we're going to multiply this by 2. Just to get rid of that 1/2 on the one side. That'll leave us with the equation 2 times the displacement is equal to velocity initial plus velocity final times change in time. And then we are going to divide both sides of the equation by the velocity initial plus velocity final portion of this in order to isolate time. Because remember, we're trying to solve without time, so we need an equation that is solved for time to plug into another equation. So when we do this division, this cancels, and we're left with the equation change in time is equal to 2 change in displacement divided by velocity initial plus velocity final. That's our little equation friend there. So, oh, I didn't mean to exit the editing mode. I just wanted to wipe my screen. I guess I accomplished that. Next, we're going to sub in that 2 change in x over velocity initial plus velocity final for change in time in the expression velocity final is equal to velocity initial plus acceleration times change in time. I'm going to write that a little neater. So we're subbing this whole mess in for time over here. I guess this is where we will pick up on Monday, because we have a ways to go yet.